Hello, welcome to Business Statistics. In this lecture, I will talk about statistical process control. Consider any process. It will have a variability. So any process will have two kinds of variabilities. One is natural variation. So this is also called normal or common variation. So this variability occurs because of nature. So suppose if you have a statistics class, at 2 p.m. on Mondays. So you would have observed that it's very difficult for us to arrive for the class exactly at 2 p.m. So you might have arrived to your class at around 1:58 p.m. or 1:59 p.m. Sometimes you would have arrived at 2 p.m. but not all the time, or 2:01 or 2:02 p.m. So this is natural variation. This is you cannot control it, so it's not controllable. So the other kind of variation that occurs in processes is assignable. Variation. It is also called special cause variation. So this is you can assign the variation to a reason. So you can assign the variation to some reason or cause. So for example, if your statistics class is at 2 p.m. and a student shows up consistently at 2:30 p.m. So in this case, you can assign the variation to some reason. Maybe the student might have got out of the job late, so that can be an reason. So there might be some reason for the student to come late, so that is assignable. So our goal is to remove assignable variation in processes. So we are the goal of the entire statistical process control is to control the variability in process. So this can be done by removing the assignable variations and such that we are only left with natural variations. So control charts are one of the ways how you can kind of remove, monitor the process. So we will use control charts to monitor the process and control the variation. So a control chart so this is sample number. You take different samples from your population. So this is sample 1, sample 2, sample 3, sample 4, and then this is measure. So a control chart will have upper control limit, which is U. So we will represent it by UCL. So from now onwards I will be writing upper control limit as UCL, and then we will have a lower control limit. So that is LCL, and then we will have a center line. So this is the mean. So now if we plot our data points or sample, we can plot them something like this. So if all the data points are within the upper control limit and lower control limit, then the process is in control. Otherwise the process is out of control. So if you see here, this point is out of the control limit, so out of the upper control limit, so this process is out of control. Suppose if this point would have been somewhere inside, somewhere maybe here, the third sample, then the process has become, the process is in control. So this is the basic concept of statistical process control. Now we will try to understand what are XBar charts and R charts. So we have XBar chart and then R chart. So XBar charts are used to monitor mean of the process. R charts, as the name specifies, it's called range. So range is, you might know the definition of range, which is largest minus smallest. Well, so this is used to monitor the variability in the process. So we monitor variability in the process. Suppose we have a process where we are filling 1 gallon of water in a bottle. So one of the things that can happen is we wanted to fill exactly 1 gallon, but it's not possible because of natural variation. We will try to we might fill nearer to 1. So we wanted to capture whether we are, how much we are shifting from this 1 gallon. So for that we wanted to capture the mean of the process. So one of the ways how we can capture the mean is through XBar charts. Suppose we have this is the upper control limit of a process and this is the lower control limit of the process, and then this is the mean of the process. So the population mean is represented by mu. So what we do is to analyze such process, every 2 hours we will take a sample and check whether they fall within the control limits. So if we take at the end of the second hour a sample, so this is sample 1, and we get so our distribution of those samples should lie within the control limits. So this would be our, for sample 1, x1 bar, or it would be nearer to the mean. So for the second sample, if we take suppose the mean is here somewhere, that is x2 bar. So different samples will have different means, but they will all lie nearer to our population mean. So if we take, so this is sample 2. Suppose we have a sample, another sample which is k, sample k. So we take k samples. And then we have our mean somewhere here. Maybe outside the control limit. So maybe somewhere here. So this is xk bar. Because this is the kth sample. So sample k. So clearly, if we start taking different samples, and here the process is going out of the control because the mean is out of the upper control limit, so we can go back to our process and look what is happening wrong in the process. So that's how we track different processes means. So this is represented by XBar chart. So the change in the means is represented by the XBar chart. So we are trying to see the changes. So if this is the process, then because we have a sampling distribution, we took different samples. This mean mu can be represented by mu x bar, or some books would use x double bar. So this is equal to, this would be equal to the summation of different means divided by k. So that's the average. So that would be equal to x1 plus x2 plus so on until xk divided by k. So again, here sample 1 means we are taking a sample of size n. So the sample size would be n would be the sample size. So once we have this, here one of the assumptions which we made is the sample will follow a normal distribution. So this is the assumption we are making. Obviously then we will have a standard deviation or the standard error. So the standard error of sampling distribution, again different samples we are taking, so it would be represented by sigma x bar. And as you know from your statistics previous topics, the sampling, if we have a sampling distribution and if the population standard deviation is known, then the sampling standard deviation or the standard error would be represented by sigma over root n. So if population standard deviation is known, So this is population standard deviation. So the formula for the control limits is what we are trying to determine here. So our formula for lower control limit, that this is XBar chart, is given by mu x bar minus 3 sigma x bar. So that can be written as x double bar, which is grand mean, plus or minus, so this is also called grand mean. Okay, so this is, since we are doing lower control limit, we just have minus. So this is minus 3 sigma by root n. Similarly, upper control limit would be mu x bar plus 3 sigma x bar, so that is given by x double bar plus 3 sigma by root n. So in real world, knowing sigma is rare, so it's very rare. So we will try to change our formula and use a different formula. So the lower control limit would be x double bar minus a r bar. So we are using range. So this is the mean of the sample ranges. A is the mean factor, and we will get this from a table. So x double bar is again the grand mean. So upper control limit, I will write here UCL. Now it will be x double bar plus a r bar. So that's the formula for upper control limit. Again, a is the mean factor and r bar is the mean of the sample ranges, and x double bar is the grand mean given by x1 plus x2 plus so on until xk divided by k. So that's X bar chart. Now we can discuss R chart. Again, R chart is range chart. So range is largest minus smallest value. So it's helping us to measure the changes in variability. So again we take our we can draw our sample diagram. So if we have the upper control limit and the lower control limit. So this is upper control limit and lower control limit, and this is the R bar, which is mean of the sample ranges. So R bar, that's actually you can say it's the population, the sample ranges mean. So the samples, if we plot different samples, all should lie within these ranges, this limits, upper control and lower control. Again, if our mean is this one, this would be our range 1 for the sample 1, and this is range 2, R2, and then if we have, so if the process is going out of control in this case, what happens is the variability starts increasing. So if you see, so we have more variability, so the process is going out of control. As you know from our empirical formula, that around 99.7, if we consider 3 sigma, should lie within this range. So once we have this, we can set up the range formula. For the upper control limit and lower control limit. So our range formula for the upper control limit, UCL, would be R bar minus 3 sigma R. This is lower control limit. And the upper control limit would be R bar plus 3 sigma R. So R bar, as you know, it's the mean of the sample ranges. And then sigma R is population standard deviation of sample ranges. Again, here also this is very rare. So population standard deviation of the sample ranges is very rare to obtain in real world. So we kind of change our formula, and we will use our lower control limit is given by D3 R bar, and our upper control limit is given by D4 R bar. So D3 and D4 are, so D3 would be the uh, the lower range factor, and D4 is upper range factor. So this is how R charts work. So this is R chart. So to summarize X bar and R chart, I will try to write the both the formulas here. And so our X bar chart, the lower control limit would be X double bar minus AR bar, and the upper control limit would be X double bar plus AR bar. So both the A's can be obtained from a table, factor table. So for R chart, LCL lower control limit is D3 R bar and upper control limit is D4 R bar. So again, A is called mean factor, D3 is lower range factor, and D4 is called upper range factor. So that's these are the formulas which we will be using to solve our problems. So let's move to the new sheet and try to solve a problem on X bar and R chart. So this is X bar and R chart problem. So suppose if we have a production process, again we will take the same example, and we wanted to fill 1 gallon of water in a bottle, right? So we are trying to fill 1 gallon of water in a bottle. So we take samples. So every 2 hours we observe, we inspect our water bottles, take certain samples and observe whether we are filling 1 gallon or not. So we have at the end of the second hour, so we will take sample 1 and then we have observation 1. So observation 1 I will write O1, and then observation 2 O2, observation 3 O3. So at the end of fourth hour we will take sample 2, so at the end of sixth hour we will take sample 3, and then we will take at the end of 8th hour sample 4. So sample 1 at the end of the second hour we check each of the bottles, and we see that the bottles are filled with suppose 1 gallon. The first bottle is filled with 1 gallon and the second bottle is filled with 0.99, and the third bottle we fill it with 0.97. So second sample we observe that the first bottle is filled with 1.001, and then the second bottle is 1.01, and the third bottle is 0.991. So third sample, which is at the end of sixth hour, we observe bottle 1 has a weight of 1.02 gallon, and then second bottle has a weight of 0.98, third bottle we have 1.003. Sample 4 0.993, 0.992, and then 0.99. So we wanted to set up our control limits for XBar chart and R chart and see whether our process is in control or not. So I will write the formulas for XBar chart and R chart. So XBar chart, the lower control limit is equal to X double bar minus AR bar, and the upper control limit is X double bar plus AR bar. So the next R chart, our lower control limit is D3R bar and our upper control limit is D4R bar. So you can see we need X double bar and R bar and A can be obtained from a different factor table. So let's calculate X double bar and R bar. So first I will calculate the mean. So this is I am calculating X bar. So it's not X double bar, we are calculating X bar. that is the mean of each of those samples. So the mean would be the average of these three numbers. So I will write for the first one 1 plus 0.99 plus 0.97 divided by 3. So this is going to be 0.986. Similarly, if we take the average of these three, which is 1.001 plus 1.01 plus 0.991 divided by 3, we will get 1. So for sample 3, we take the average of these three, we get 1.0001. And finally, if we take the average of these three, we will get 0.9916. So these will be approximate values as I solved this in Excel and copied down the final values. So they will be approximate values. So the next step is to calculate the range. So I will calculate the range also. So range here is R, and that is the definition of range is largest minus smallest value. Minus smallest. So that is the largest value in this is 1 and the smallest is 0.97, so that would be 0.03. So the largest value in this is 1.01 and the smallest is 0.991, so the difference of those two would be 0.019. So the largest value in this would be 0.02 and the smallest would be 0.98, so that would be 0.04. The largest in this is 0.993 and the smallest is 0.99, so that is going to give us 0.003. So now we wanted X double bar, which is the grand mean. So what we can do is we can take the average of this, this, this and this. So X double bar is equal to average of 0.986 plus 1 plus 1.0010 plus 0.9916 divided by 4. So we get an X double bar of 0.995. Again, if we want R bar, we will do R1 plus R2 plus R3 plus R4 divided by 4 in this case. So that is R bar is the average of all these numbers. So that is 0.03 plus 0.019 plus 0.04 plus 0.003 divided by 4, that is R bar is equal to 0.023. So now I will do X chart. So X bar values. So X bar chart. So the lower control limit, if you see, we have X double bar, that is 0.995 minus, now we have A, so we need A, so we will use a table for A. So if you look, we have the number of observations in each sample, that is observations are 3, so our N is 3 and our K is 4. So we used K here, so this was our K. So now we will use N is equal to 3, so we have to go to our table. So I will go to factor table and look at sample size of 3. So we have a sample size of 3, that is so I will use that row. So A value at sample size 3 is 1.023. So I will use 1.023. So this is 1.023, that's our A. So this is from table. So multiplied by R bar is 0.023. So this is going to give us 0.9714. So upper control limit would be 0.995 X double bar plus, now A is 1.023 multiplied by R bar is 0.023, which gives us 1.0185. So these are the control limits for X chart. So now for R chart. So our LCL is equal to D3 R bar. So we need, so this is LCL, which is lower control limit. So we need to obtain D3. So the D3 we can obtain from our table. So I will go to the table, and if you see our D3 for row 3 is 0. So I will say 0 multiplied by 0.023, that is 0. So upper control limit, again I have to go and look for D4. So I will go to our table and look for D4 with sample size 3. So that is the value 2.574. So that's 2.574 multiplied by 0.023, that is going to be 0.0592. So once we have these values, we can plot our XBar chart. So I will try to plot XBar chart here. So this is our this is sample number. So I have 4 samples. So this is 1, 2, 3, 4. So now I have lower control limit and upper control limit. So the lower control limit value would be 0.9714. So suppose this is 0.9714, and the upper control limit is 1.0185, and then the mean is X double bar 0.995. So now I will plot each of these mean values. So I will plot each of them in this diagram. So the first one is 0.986. So 0.986 would lie somewhere here. And then the second one is 1. So 1 would be nearer to somewhere here. And then the next one is 1.001, so it will be on the higher side. And the fourth one is 0.9916, so that would be somewhere here. So if you see all the points, if I join them, so you see all the points are within the control limits. So this is upper control limit and this is lower control limit. So all the points are within the limit, so the process is in control. So this is only the mean is in control at this time. So we have to check for the variability, which is R chart. So I will plot R chart here. Again, this is sample number. So we have sample 1, sample 2, sample 3, sample 4. and the lower control limit for R chart is 0, so I will plot 0 here, and the upper control limit, so this is the lower control limit, upper control limit is 0.0592, that will be somewhere here, 0.0592, and then this is upper control limit, and this is R bar, that is 0.023. So once we have that, maybe I will draw this in blue. So once we have that, we will try to plot each of these ranges. So the first one is 0.003, so it will lie somewhere here, and then the second one is 0.019, so it will be on the other side here. The third one is 0.04, it will lie somewhere here, and then we have 0.003, which will be somewhere here. So if you join them, again, this is if you see all the points lie within the control limits, the process is in control. So based on both are in control, so the entire process is in control. So that's one thing. The other thing is in control charts, we should also, it's not only about lying within the control limits. If there are patterns, then also the process is going out of control. Suppose we have a process which has like lower, this is lower control limit, and this is upper control limit, and then we have the center line, which is X double bar. Suppose if you consistently find points on one side, that means your process is underestimating, so there is something wrong going on. So you have to start looking for the patterns, even though it's within the control limits. This pattern tells us there is something wrong going on in the process. So always try to look for patterns also. So this concludes our lecture on statistical process control, especially with XBar and R charts. We will be discussing other charts in other lectures. Thank you.